Hey Occam students, Ben Azmon here. Today we're going to be doing our very last lab. We're almost done. It's nuclear magnetic resonance. That's right, NMR. Let's get to it. NMR. I'm not going to go too much into how it works, but essentially you put a sample inside a giant magnet that's kept really cool to make it a superconductor, and then you're going to apply a ring to it in a magnetic field, and in the magnetic field you get a spin flip. It's spinning this way, and now it's going to spin that way. As far as you're concerned, the chief way most people are going to work out what molecule they have and verify that that's in fact they're doing the correct thing. For us today, we have our set of our notes. Now, that does include IR, and if you need a brushing up on IR, I do have the previous video. Link is on the screen now and in the description down below. As for the NMR itself, for this, let's start here with a chemical shift of proton NMR, of H1 NMR. We're going to talk about carbon a bit later. The first thing I would like you to see is like this is the quick and dirty, like this is where things will show up. This is not when most of the work gets done, but if you can see something quick, you can take it out. So at 11 to even 12, you'll see kind of a rough thing at the bottom. That's usually a carboxylic acid. If what's it called? If you see a relatively sharper one, it's somewhere between 9 and 10. That's going to be an aldehyde. Those are quick and easy. Of course, both of those can be verified also by IR and carbon NMR. You'll see that there too. Then 7 to 8 is usually where all the aromatics show up, and that happens a lot. Now there's some more stuff to talk about aromatics, a few other quick ones you can see, but I want to talk about the other things first, so we'll get back to that. Next, 5 and 6, we're going to see usually double bonds. Triple bonds also show up somewhere around here, a little lower for the triple bond H. Now, of course, all of these, this is the H's on them. It's not the C's. So it's the H for each one that shows up, not anything else. Of course, it's proton NMR. So for a double bond that happens to have an H on it, that will show up usually in the 5 to 6 range. And then finally, all the way down here, this is where all the standard CH single bonds are, within reason, okay, usually between 0 and 3. Now, all of that to say can be changed depending on this. If you have an electron withdrawing group, that is to say that it has a double bond one space away from the hydrogen, from that carbon hydrogen you're interested in, that's this one. So it has a double bond one space away from that, or that is an electron withdrawing group. Nitro groups, aldehydes, ketones, a variety of those. If you have any of those, it's going to pull your chemical shift downward, and you'll have a lower than expected. If, on the other hand, you have a something with a lone pair, a chlorine, iodine, bromine, fluorine, something like that, oxygen, nitrogen, something with a lone pair there, that will be an electron donating group that will push to a higher than normal chemical shift. In particular, you'll see like something like this might show up all the way over here. That's the kind of thing that happens, and this effect happens through the entire molecule, with decreasing effect in each one. So this one, that first one here, that one might be moved up a ton, this one a little bit, and this one just a little bit more, and so it's a little bit less. So a little bit less, and so on down the line. Same thing applies to electron withdrawing, and from that you can determine where things are positioned. Okay, now getting into the more useful stuff, our next topic is integration. For this, what essentially it is, it's the area underneath a curve, and it tells you exactly how many hydrogens are in the carbon, or whatever element, that you are interested in. So it's the hydrogens on that specific carbon, usually carbon. Okay. Now this can be displayed in a few different ways. It could be that it's just listed on the top. That's a lot of the times what it's just going to be. It could be that it's given to you like this, where you'll get these kind of these kind of rows. Each one of these rows usually accounts for 1 hydrogen, and so you can see here this goes up half, and then 1.5, 2.5, 3, and so you would expect this to be 3 hydrogens. This is an older version, you don't see it as much, but it does still happen. And then the last version you might see this reported as is like this. This is that they just give you some random numbers here. And I know from experience that, oh, at this specific chemical shift, I would expect this one to be a single hydrogen. And because I expect that one to be a single hydrogen, I know that the base number is 5, and if I divide each of these by 5, then I will get how many there are really. So there's 3 here, 1 here, and 2 there. This happens, the number is usually not quite as nice and neat. This is closer to reality because in reality, the computer can't tell you specifically 1, but you can usually guess down to what you need it to be. So that's what you often do. But for your thing, most of you are going to get something that looks like this, far easier to handle, especially when you're getting started. Now, what does it mean? Well, if you have an integration of 1, okay, 1 hydrogen, this has 3, so this is 1, it's probably a CH, and it has 3 other things attached to it. We don't know what exactly, but it is a CH. It could be an OH or an NH, but those are usually quite broad. So where something like this might be sharp like that, the NH and the OH end up being kind of fat. This one is usually also taller. This one's going to be kind of stumpy. But these two can also, for these two, these can show up out of a wide variety of ranges, so I didn't include them in the chemical shift, but they do happen. So just be aware, it's a little less common for your problem set, the most common being it's just a CH. Then 2, of course, CH2. Now, once again, can be less common. So this is each peak is how many chemically identical H's there are. And so for these two, obviously these two are identical. They can spin, they're interchangeable. You can't tell them apart. However, if you have 2 symmetric CH's on 2 opposite sides of the molecule, if they can be interchanged that way from the whole molecule spinning rather than the individual bond, those do show up as well. So be aware if you see 2, it could technically be 2 CH's. Now, 2 H, if it is integrated 2, it could be 2 separate CH's. And 3, of course, CH3. 4 is commonly, if you get it, it's going to be 2 symmetric CH2s. Uncommonly, it's actually methane. This should not be in your thing, but it could happen. This is going to be a really low chemical shift. So this is very unlikely, but does kind of. 5 is not really a thing that happens. 6 is usually 2 symmetric CH3s. That's quite common. You'll see that all the time. If you think integration of 6, you should think that you have usually an isopropyl group that you might see here. Now, I suppose you could also have 3 symmetric CH2s, but that's very unlikely. Next up, and one of the most useful, is multiplicity. For this, what we're actually looking at is not the hydrogens that are on that peak, on the specific carbon, but we're looking at the neighboring hydrogens. In general, the formula goes that the number of hydrogens on the neighboring peak is equal to the number of peaks minus 1. So, this is our spread of the few different kinds. We have here the ratio of the heights. We'll talk about that in a moment. The name, the abbreviation, how many hydrogens are on the neighbor, and then some common versions of that. So for us here, simplest version, there's 1 peak, therefore no ratio between the peaks. This is called a singlet. This is abbreviated S. Of course, 1 minus 1 is 0, so there is no hydrogens on the neighboring carbon. Who knows how many hydrogens are here? That depends on integration. This could be any one of the ones we had before, but the neighbor, its adjacent ones, have no hydrogens on them. And for that, the common versions are, it's right next to a quaternary carbon, it's right next to an alkyne, very common it's right next to a carbonyl, or it's right next to some kind of atom that doesn't have a hydrogen on it, like an oxygen or nitrogen. Even if those technically do have hydrogens, if they don't have carbons on the other side, they usually don't cause multiplicity just because the angles aren't quite right for that to happen. Weirdnesses do occur, but in general, they don't split each other. So they don't cause this kind of weirdness happening. So if there's an O or an N, what's on the other side? We don't care usually. Or at least it doesn't show up. So, next one, 2 peaks, okay? Ratio 1 to 1, they're going to be roughly the same height, called a doublet, D, 2 minus 1, there's 1 hydrogen on neighboring carbon, usually it's a CH. Okay, once again, OHs and NHs don't usually show up, and so they won't usually cause splitting. They will show up as a singlet, as a whole, if you have a CH or an NH, and it doesn't matter what's next to it. Next, 3 peaks, okay, ratio 1 to 2 to 1. You know, this is, I think it's Pascal's triangle, whatever. That's a kind of setup that ends up happening. That means that this is twice as tall as those, roughly. This is called a triplet. T3 minus 1 is 2 hydrogens on the neighboring. That means it's probably going to be a CH2. Technically, you could still have symmetric neighbors, which each have a CH, but that's unlikely, for at least for the things we're going to give you. Next, we have a quartet, 1 to 3 to 3 to 1, that's 4 peaks. That means that this peak is the tall peaks are about 3 times taller than the small peak. If they're all the same height, that's something completely different. We'll talk about it in a bit. But if they have to have this ratio, okay, that's a quartet. Okay, 4. Okay, Q is the abbreviation. 1 minus 4. All of these are backwards. Lovely. What a lovely waste of time. Okay, now that I fixed that, 3 minus 1 is 2. Okay, it's usually a CH2. For here, 4 minus 1 is 3. That means this is usually a CH3. It's a pretty good sign. In particular, often you'll see these two together because you might have an ethyl group, so it's a CH, it's a CH2 and a CH3. Then this one is the next interesting one. Is a septet that's 7 peaks. They're usually really tiny. You need to like enlarge it to see it. But the ratios, again, you can look up the triangle. I'm not going to bother. It looks triangular. This is a septet, there's 7. There's a lot of abbreviations, the most common of which is ST, but you'll see a few of these. It's usually S with something else. 7 minus 1, that's 6. Those are 2 symmetric CH2s. 2 symmetric CH3s. This is very common in an isopropyl group. In particular, those show up. Next, if it's just a mess, and that happens because guess what? If it's not symmetric, and you have multiple things, they're going to lay on top of each other, and you're not going to see that. For that, we just call it a multiplet. We put an M, and as I said, it can be lots of different things. On this side here, I have complex splitting. That's these ones. These are more sophisticated things. They show up less as for you guys, but I do want to tell you that it does exist, and that is if you have a non-symmetric set, so there's a neighbor on either side of you that has a hydrogen, you might see that individual one has multiple splittings. In this case, if this has 2 and 2, this is a doublet of doublets, and so 2 minus 1 is 1, and 2 minus 1 is 1. So these are 2 CHs, which are not symmetric. If they were symmetric, then they would show up over there, okay, in one of the earlier ones. But if they're non-symmetric, they both split it, and in different amounts, so you get multiple splittings. Of course, you can layer any number of these as you like. This is a doublet of triplets, DT, 1 and 2, and so this is non-symmetric, a CH and a CH2. Obviously, those can't be symmetric. All of this is the main things that you use. I'm going to show you how to use it in just a moment. The last thing you should know is that in general, they will slope up to what is causing them to split. So in this case, this is sloping up to the right, so we would expect the thing that split it to be on its right. Same thing here, that's up to the right. Here you can see that again, that's up to the right. These for a septet, it's a little harder to see, but once again, it is these ones that you care about. multiplets you can't really see. And for here, for a doublet of doublets, you can see that this one slopes up to there and that one slopes up to there because they're splitting each other. And the same thing here, this should be like that technically, and that to that, because they're splitting each other, so they go up and towards each other. Okay, one more word here about aromatics. For these ones, there's 4 main ones that you'll see for this kind of thing. And they have specific integration, like the pattern you'll see, and then what they actually look like, and then what they're called. So if we have an integration of 5, of course, this is for aromatics, so this is between chemical shifts 7 and 8. If we have an integration of 5, and it's a mess, it's a multiplet, you don't even want it to touch it, it's ugly, but it has 5 H's in that region, you're looking at a phenyl group, okay? You have one connection to the aromatic ring, and the rest are hydrogens, and they overlap each other. Now, sometimes you can distinguish a little bit depending on what other groups you have here, but in general, if it has 5 things, regardless of how complicated or simple it looks, it's probably phenyl group. As 4, we have 3 different options here. So for us, if we have the nice clean doublet of doublets, that's real easy. That is just going to be a para position right here, so that they're opposite each other. And the reason what you'll see here is sometimes you'll see this as an integration of 4 for everything, or you might see it as 2 H's and 2 H's. Either way, para, these are opposite each other. Next, if you see an integration of a singlet and a multiplet usually, that and this here, and you'll either see this integrated as 4 or as 1 here, 1 hydrogen there, and 3 hydrogens there. That is going to be meta. There are 1, 3 to each other, 1, 2, 3. So there's 3 hydrogens here and then 1 by himself. This one is almost always going to be higher just because it has those extra pieces right there that separate it. So of course these are other connections that are not hydrogen. That's what that's meant to symbolize. So here, this guy's usually higher up. As you see, either 3 to 1 or 4 with this pattern. And for here, if you see an integration of 4, and it's wholly unreadable, usually to the low end, it's some kind of multiplet. That is as a whole going to be the ortho 1, 2 to each other, and those 4 hydrogens all on the same side. Now switching over to carbon-13 NMR, we have a few things to discuss here. First is that it's basically all chemical shift. There is no multiplicity, there is no integration, but mostly. It's essentially all chemical shift. And you can, in general, figure out exactly how many carbons you have, just like technically you can figure out how many hydrogens by literally counting the total integration. You can figure out how many carbons you have by counting how many peaks you have. But these are, of course, unique carbons. So if you have symmetric, they will show up in the same spot. So that'd be 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12 for our kind of nonsense thing here. Ignoring, of course, this. This is the only kind of splitting you'll ever see. This usually happens at 77. This is just a solvent. It's a triplet-looking thing. Just ignore it if you see it. But in general, you have these, and mostly they're all the same height, with the exception of if you have a symmetric something, they may in fact be twice as tall. If you have 2 of them, 3 times as tall. If you have 3 of them which are symmetric, this isn't a perfect thing. You're kind of like waffling because sometimes it's going to be in the middle and it's going to be like, is this really, is it not? So that might indicate that, and you always put it as an asterisk. That might mean that there's a symmetric set here, or it might not. And then for these guys, the really late ones, those are always tiny. So those are quaternary carbons. In particular, from above 200, 200, 220, those are aldehydes and ketones. And then 160 to 190-ish is where you have carboxylic acid, esters, amides, acyl chlorides, a variety of other things. And those are all, of course, those are tiny little things. You're not going to see much of them. Next is in the big bulk here from about 100 to 160 is where double bonds show up, as well as aromatics. Of course, aromatics are double bonded, and so that's what you'll see. In particular, I have here 2 examples of aromatics. For an aromatic ring, regardless of what's on it, you almost always, assuming there's anything on it, like if it has one group, then you'll have it, or more, you'll have this pattern. If there's no groups, then it's just one line. But if you have at least one group, you'll usually see 2 of them tall and 2 of them short. In this case, you see the order doesn't matter. So it could be tall, tall, short, short, or short, tall, tall, short. Whatever order doesn't really matter. But for an aromatic thing, you see 2 tall, 2 short, because you always have these 2 will be symmetric, so they will show up together, and these 2 will be symmetric, they'll show up together, and then this will be independent, and that will be independent. And so they might show up like this or that, and that depends on, as before, electron withdrawing and donating groups. Electron withdrawing groups lower your ppm. Electron, that's a unit here. The electron donating groups raise that. You have a higher chemical shift in general. So if you have an electron donating group here, you'd expect this one to be higher, and you'd expect those 2 to be higher in a variety than the ones next to it. Because of course it transfers multiple steps down as well, each time a little less. Last couple here is over here we have triple bonds, which are rare, but you'll see them in the 70 to 90-ish range. And then every other kind of single bonded thing is from 20-ish to 60, 70-ish. You don't really see that low because, of course, below 14-ish, 12-ish, that's where hydrogen NMR is, so you're not going to see that in carbon NMR. The next part of carbon NMR is these 2 additional kinds of tests called depth 90 and depth 135. There is a ton more NMRs you can do, but as far as you're concerned, these are the main ones. Now, how they differ from regular carbon is a regular carbon will show quaternary CHs, so aldehydes, ketones, or just something that has 4. It'll show CHs, CH2s, CH3s. Sorry, quaternary Cs, not CHs. Of course, there's no H there. It can't be, then it's quaternary. And we'll show them, and it'll show everything up. Okay, it's just like this. They're all facing up, just like you would expect them to. However, for depth 90, okay, depth 90, you don't see quaternaries. They just vanish. So that means that this one here and that one there were most likely quaternaries. We expected this one to be quaternary anyway, just because of its position. But that would tell you that's most likely a quaternary. However, you'll see there's a few other missing peaks. The other things that are missing are CH2s and CH3s. Only CHs appear for a depth 90. So depth 90 only gets CHs and no CH2s, no CH3s, and no quaternaries. So you see these are gone too. And then for depth 135, again, no quaternaries. But this time we do have the CH, CH2, CH3, but CH and CH3 are both going to be facing up, where weirdly enough, CH2s are facing down. So using all of this pieces of information, you can figure out what something is. So if it's only missing from 135, then that means it's a quaternary. That means that that one is a quaternary and this one is a quaternary. If it is missing from, if it's down in the 135, then that's definitely a CH2, no question about it. If it's present and up in the 135, but absent from the 90, that should be CH3, which means everything that's left here that's only in the 90, those are all CHs. That tells you a lot about a molecule and allows you to figure it out. Now, how do you apply all of this into one thing? Okay, so this is one of my favorite examples to do. This involves all of this data, okay, for our compound, and they're all the same compound. This is the type of thing you might see. For us here, of course, this is our IR, this is our HNMR, and this is our C13 NMR. Now, starting with the IR, quick, brief things. We see two peaks somewhere below 3,000, that means we're probably here looking at CHs. Okay, there's some kind of single bonded. Okay, now that could be CH, CH2, CH3. Regardless of what it is, it's single bonded. That's the important thing. Because it's not high enough to be double bonded. And then we see another one, 1750. That is some kind of carbonyl. Okay, so we know that we probably have some kind of carbonyl. And then there's some mess down here that's pretty low. We don't pay attention to it. That's part of the fingerprint region. For our hydrogen NMR, already quickly looking at it, we can see we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We're going to have 12 hydrogens total for our thing. So we expect that our formula will be something in the ways of H12. And for the carbon, we see 1, 2, 3, 4, 5 carbons. So that probably is 5, but that's not guaranteed. Remember that we can't have symmetric. We don't know if these guys here are symmetric or not. So this is 5 maybe. Okay, we'll see about that, if that makes sense for it to be 5. Now, back to the hydrogen NMR. Now, what we would like to see for something like this is, I like to make a table like this. This table is just a manifestation of how a chemist thinks about it. It's easy for you to use when you're starting out. Later on, you do most of this in your head. But for this, for our first peak, and I labeled the peaks A, B, C, D, I have 4 peaks, I find it easier to talk about and to think about if I have a label for them. So for A, we know how many hydrogens are on it. Oh, we have 1. That's easy enough. For B, we have 2. It is literally given, so I'm just copying it down. For C, it's 6. And for D, it's 3. That's easy enough. And as we said before, what is this most likely? Well, most likely this is going to be a CH of some kind. Okay? And this is a proper CH. It's not just any single bonded. This one's going to be most likely a CH2. And this 6, remember, can you guess what it is? Yep, that's 2 CH3s, 2 symmetric CH3s. And then here, once again, we see another CH3. Remember, this is integration. Integration is part of what is actually on that peak. It's that one. Then, looking at this quickly for multiplicity, okay, that's what all of these are. These are multiplicity. Multiplicity for the first one, here we have 1, 2, 3, 4, 5, 6, 7 peaks. It even says they're septed. So that's 7 peaks. That means that the hydrogens should be 1 less than that. That means 6 hydrogens on the neighbor here, because it's always -1, regardless of what it is. It's always -1. So that makes this a little easier to interpret. Then for B, that's a quartet. That's 1, 2, 3, 4. So that means we have 3 hydrogens on the neighbor. Remember, all this is the neighbor. And then here 2. So that means we should have 1 hydrogen on this neighbor. And here's the triplet. So a triplet is 3. That means this should be 2 hydrogens on the neighbor. What this means for us here is most likely what this is for this one, 6, just like before. That's 2 CH3s. 2 CH3s. And here for 3, that's a CH3. And here for 1, that's a CH, a proper CH, not just single bonded. And then this is a CH2, because we have 2 here. So for this, we can already see a pattern emerging. And that first pattern is that this is a CH that sees a CH, 2 CH3s. And this is 2 CH3s that sees a CH. That means that A and C should be next to each other. And I'm going to put C on the outside because those are terminal. So what that might look like for us is something like this. Here's our CH3, here's our CH3, and we're connected here to our CH, which has 1 more connection. There's 3 connections here. We need to make 1 more connection. What else do we see? Well, we see over here, we see over here, well, this is a CH2 that sees a CH3, and this is a CH3 that sees a CH2. These two are probably paired up, and so what we would expect is we would have D and B together. Once again, I'm putting D on the outside because it's a terminal, so that would make it for us here that our D, CH3, is there, connected to a CH2 with one more connection between them. Now that already has 1, 2, 3, 4, 5 carbons, okay? Now, for this, I did make a little weirdness here. So for our carbon, I made a little correction here. This one is in fact twice as tall as it should be because we do have symmetrical. You of course won't be doing corrections. I'm just working with this quickly off the fly. But we can see here that we actually, it could have been 5, but it could have also been 6 if that was a double. Even if you didn't see that, even if you, and I made it nice and clear now, but it's not guaranteed that you're going to see it every time. That's why I put a question mark. So at the moment, it looks like there should be something else here because we know we have a carbonyl. Carbonyl wouldn't show up here, especially unless it was a carboxylic acid. We don't have anything to be a carboxylic acid or an aldehyde, as the other one's carbonyl. So it's not that, so it has to be some other kind of carbonyl. So that carbon, we can see here, we also have something that looks like a carbonyl. That's not an aldehyde or a ketone, okay? So that means that this is most likely an ester. So that's what we're going to go with here. We're going to go with this here is probably an ester of some kind. So we need to have connections on either side. Now, just to confirm from all of this, we can see that here that from our information we have 5 here. These are all kind of single bonded things. That's most likely a carbonyl. And over here from the depth information, we can see that, okay, these are both gone, so that's definitely a quaternary, so that doesn't surprise us. So we expected a carbonyl, most likely an ester, because the position is too low to be an aldehyde or a ketone, so ester is the most likely. But of course, these can be other things. You do want to look at your problem given, or sometimes you're given additional information that will say, oh, this is definitely an ester and not an amide or something like that. I'm going to say it's an ester because I made up the problem and I know that it is. For us here, 50, so here it's present in depth 90 and it's up in depth 90. Okay, that means that in depth 135, that means if it's present there, that must be a CH. Okay, there's no other option. Here, these are all absent, and these two are up, so these have to be CH3s, okay? So for this one over here, for these two, we can see that the depth 90 is absent, but they're both up. That guarantees that these are supposed to be CH3s. That's these ones here, and that this one here, what's it called? This one in the middle, because it's down for depth 135, that should be a CH2. Yep, I wrote 3. This should be a CH2. Now, that should tell us already, most likely, where these are going to be. Now, for us, we know that we're going to have an ester, and we know that we have these. So, for our compounds, when we label them, notice that I labeled here, we need to kind of figure out how to put in our ester, and then we'll label these in a moment. But they all line up with what we already expect. So our ester, we have 2 options. Our 2 options is we can either put it this way, or we could put it this way. Yep. So we can put it either way, and we kind of have to figure out which one is better for us. And for this, because if we put it in that way, this one will be closer to electron withdrawing, this one closer to electron donating. We would expect this to be high and that to be low. If we put it in the other way around, this is next to withdrawing, so it'd be low. This is next to donating, so it'd be high. So whatever one's our highest one should give us away. And for us, A is in fact our first one. That is this one. So we would expect this to be in this order here to actually solve all of our molecule. So that's our molecule for this. And so we can get rid of that. We don't need this anymore. This is our molecule as we anticipated. Our last thing we also have to do is we have to redraw this molecule one more time. CH3, CH2, C double bond O, CO, CH, and then CH3. And then we want to label these with some kind of labeling scheme. Now, if your paper gives you a specific labeling scheme to follow, label as they say in the paper. If it doesn't, choose whatever labeling scheme you want. I'm going to use lower cases in this particular case, A, B, C, D, and E. And so, of course, this is A, B, C, D, and E. Now, for us here, we can already figure out, okay, well, this is the ester, that's the A, that's nice and easy. The CH2, okay, that's C, that's nice and easy. Then 22 here is twice as tall, and so we would expect that to be these guys over here. So that's 22, which we call D. That means these two are going to be D. And between these, we said that this is a CH3 and that's a CH. So our CH has to be B, and this has to be our remaining one here, which is A, B, C, D, and E. So that's E. That's also the other way we can figure this out is we know that the closer you are to a group, to the main group, the center, you should have a higher proportion. So between these two, you would expect that these two CH3s that we want to distinguish between D and E, that this one, which is closer to an electron donating group, should be higher up than this one, which is closer to an electron withdrawing group. And we see that here, that between these two CH3s, D is higher up than the E, and therefore this too should be D, and this should be E. You want to fill all of this out in your form. So these are the hydrogen assignments with each unique hydrogen, and these are the carbon assignments. Make sure you also give me if this is a CH2, CH3, CH3, what is it? What group is it? Is it an ester? Whatever. That's it. You're done.